Along with leaving group characteristic, nucleophile characteristic in an SN1 and SN2 mechanism can be very important. Let's go ahead and look at this. Now, the nucleophile we have seen can either be neutral or uncharged, but it must have non-bonding electrons that allow it to do nucleophilic attack. There is something that we call nucleophilicity that measures how nucleophilic something is. So it's basically measuring how much the nucleophilic atom is attracted to the carbon with its large del positive. The concentration of the nucleophile is important, but only in SN2. Because it is not in the rate-limiting step of SN1, the concentration of the nucleophile does not matter, nor does the characteristic of the nucleophile matter. So let's go ahead and look at an SN2 reaction. In an SN2 reaction, this is the rate equation. Notice it has K times the substrate concentration times the nucleophile concentration. So the concentration of the nucleophile is very important to determining the rate of the SN2 step. But in the SN1 step, no nucleophile is in the rate determining step, and so the rate of the reaction is independent of the nucleophile concentration. So high nucleophile concentrations give faster SN2 reactions, but it does not change the rate of SN1 reactions. The nucleophilicity of the nucleophile is very important in SN2 reactions, but it does not matter in SN1 reactions. Why? If I make this nucleophile in an SN2 rate more nucleophilic, that means that it lowers the energy of the transition state, and so the K value will be bigger. But because there's no nucleophile in the rate determining step, the nucleophilicity of the nucleophile can be very poor, and that rate of the nucleophile attacking to, or jumping onto the carbocation is going to be faster than the unimolecular rate determining step, the first step where the carbocation is formed. And it's going to be faster than that. And so it won't matter if it's highly nucleophilic or non-nucleophilic. So what do we know? Highly nucleophilic nucleophiles give faster SN2 reactions, but they have no effect on an SN1 reaction. How do we know what is the nucleophilicity of something? Well, we know the nucleophilicity of a nucleophile increases with negative charge. In other words, if you have a negative charge on your nucleophile, it's going to be more nucleophilic than if you don't. So if I look at these two similar nucleophiles, here this is methanol that's been deprotonated, and we call it methoxide, and here is methanol. They will give identical results in a nucleophilic substitution reaction. However, this one has just a non-bonding pair and no negative charge, whereas this oxygen has a negative charge in addition to a non-bonding pair. This is a better nucleophile than this uncharged methanol. Why? Because that negative charge is going to be more attracted to the electrophilic carbon in the substrate. Right here, this is methanethiol, and this is called methanethiolate. Methanethiolate is a better nucleophile than methanethiol. Why? Because of the negative charge and its increased attraction to the carbon with the del positive on it. Hydroxide is a better nucleophile than water. Chloride is a better nucleophile than protonated chloride. So anytime you see a negative charge, you can think, well, the SN2 reaction should be increased. As the size of the atom increases, the nucleophilicity increases. So those atoms that are larger atoms are more nucleophilic. Now, this is only when comparing atoms in a column. So this is not like comparing oxygen to nitrogen or carbon to oxygen. The larger atoms, lower in the periodic table, are better nucleophiles. This is because the larger atoms have more polarizable electron clouds. And so as the electrons are farther away from the nucleus, and as the atom comes into the carbon, those electrons are farther from the nucleus, so they reach the carbon before they start encountering steric hindrance. And not only that, those electrons are polarizable. So as the atom moves into the carbon, the electrons in the orbital start reaching out to form the bond because they're very polarizable. Why are they polarizable? Because they are farther from the nucleus and they can distort more readily because of less attraction to the nucleus. So if I look at sulfur versus oxygen, the sulfur will be a better nucleophile than the oxygen, whether it's negative, comparing negative to negative, or comparing neutral to neutral. Iodine is a bigger atom, so it is a better nucleophile than either bromide, or chloride. So here is a chart that summarizes what we just saw. You can see on the right are negatively charged nucleophiles. They're the good nucleophiles. On the left are the neutral nucleophiles. They're poorer. On the right, you have the big atoms. On the left, you have the smaller atoms. And so you can see that this trend goes exactly as we discussed. And this might be a useful chart for you to look at once in a while. But just use those trends that we've been talking about so far, and you'll be able to determine things about those nucleophiles using size of atom and negative charge. Now, the book emphasizes the nucleophilicity of the halides as nucleophiles. And of course, what are you going to see? Iodine's better than bromine, which is better than chloride, which is better than fluoride. So keep that in mind as you're doing that, but it still holds true for the other nucleophiles, the things that we just discussed. Okay, so now on this question, try to figure out which would be the faster reaction here. Okay, we look at this reaction and we can see it is a primary carbon. We remember that primary carbons undergo SN2 reactions. Then I look and I see that these are the nucleophiles that are different, is that this is the poorer nucleophile, this is the better nucleophile. So which one would go faster? The nucleophile matters here because it's primary. So this is the better nucleophile, so this would be a much faster reaction. So what would we see? We would see that the thiol would form faster. So which would be the faster reaction here? If I look at this reaction, I look and I see this is tertiary and this is tertiary. A tertiary carbon is certainly not going to undergo an SN2 reaction. It will undergo an SN3 reaction. So if I look at this reaction, this is going to be independent of the nucleophile. So if I look at the outcome of these reactions, they're going to occur at the same rate. Why? Because the characteristics of the nucleophile will not matter. So which of these reactions is faster? If I look at these two reactions, determine what is the difference and which one would be faster, if either. Well, I look at the two compounds and I see that they're both methyl iodide. And so I'm not going to be considering SN1 conditions. I'm going to be considering SN2 conditions. Here, the characteristics of the nucleophile matter. So I look at the nucleophile and I see that this one has a negative charge and this one doesn't. Because the negative charge makes it more nucleophilic, which is going to be the faster reaction? The first one is going to be faster. Which reaction is faster here? Well, if I look at this reaction, I see it's a tertiary halide. Tertiary halides will go by SN1. I am increasing the concentration of the nucleophile, but the concentration nor the characteristic of the nucleophile does not matter for SN1 reactions. So what would I find? The reaction would go just as fast with either one.